Okay, so the next two here are actually pretty much identical to that first one that we just did at the end of the last part of the video. So here we have, they're telling us a little story about rhubarb, rhubarb's sour taste. So we have a solution of oxalic acid. What concentration should appear on the label if the pH of the solution is this? So I'm not going to show every single step here just because it is so similar to the other one. But because of that pH value, the hydronium concentration at equilibrium should be 0.282 moles per liter. So what ends up happening is if we set up a Ka expression, it's going to be x squared, oh, pardon me, not x squared. It's going to be this value squared, 0.282 squared, and then we're going to have, okay, and then we're going to have x minus 0.282. And then this Ka value, we can look this up for oxalic acid, which is 5.9 times 10 to the negative 2. Okay, so when you work this out, your X value that you get is 1.6299 moles per liter after you factor that out. And then this has to be two significant digits, which is 1.6. Number 3, again, very similar. So we have nitrous acid, which is in acid rain. It gives us the pH. We want to know the concentration of the acid. So by doing 10 to the negative 1.85, our hydronium value here is 0.0141 moles per liter. So our Ka is going to be 0.0141 moles per liter squared over X minus that. And then the Ka value for nitrous acid you can look up in your table, which is 4.6 times 10 to the negative 4. So when you factor this out and all said and done for your X, you should get 0.446, I believe. And it has to be two significant digits, because remember it goes by decimal points. Did I do that for the last one? Oh, no, I didn't. Oh, yes, I did. Sorry, pardon me. So 2, so this should be 0.45 moles per liter. Okay, so this, now we're going to look at the third type of questioning here where you have the initial and you have the pH value, but you have to calculate the Ka value. So in other words, we have enough information to put into the ICE table and into our Ka expression to solve for Ka. Okay, so again, this first one I'll do more in depth, and then the second one I'll go a little bit faster because it's very repetitive. Okay, so we have vitamin C, which is essentially ascorbic acid. It prevents scurvy, tells us a little story. We love our stories, right? So anyways, let's get to the bottom of this. We have a 0.100 mole per liter solution. So this is our HA initial, right? And we have a pH of 3. So from this pH, we can get the hydronium concentration at equilibrium by doing 10 to the negative 3, which is essentially 1 times 10 to the negative 3 moles per liter. And we want to calculate the Ka. So I'm going to use just our simple HA expression here to do our equilibrium. So you can, just a reminder of how to set this up. AQ, and then this guy is liquid, AQ, AQ. Right? So our original here is 0.1, which would then be 0 minus x, 0.1 minus x, plus x, plus x, x, x. Okay, so we're solving for Ka. So in this case, this is going to be x squared over 0.1 minus x. Now we have x. Remember, by them giving us the hydronium at equilibrium, that is equal to x. So we have the numbers here to plug in. So this is going to be 1.0 times 10 to the negative 3 squared over 0.1 minus that. Right? So we can solve for our Ka. So in this case, our Ka value ends up being 1.01. Let me just check my sig figs. 1.01 times 10 to the negative 5, which technically we need 2 because of the 2 decimal points on the pH. So these should actually just be 1.0 times 10 to the negative 5. Okay. So number 2 is very similar. So we have lactic acid. It's in sour milk, which gives us our sauerkraut taste. Again, our little story. So we have the concentration initially. From this pH, we can get the hydronium concentration, which is at equilibrium, 1.778 times 10 to the negative 3 moles per liter, and then calculate Ka. So in exactly the same way we just finished saying in the last one. So this is our X essentially squared over our initial concentration minus our hydronium, or our X. So we should end up getting a value here of, we need 2 sig figs. So it's going to be 1.4 times 10 to the negative 4. Okay, so let's take a look at weak bases. So that was a whole bunch of different work that was incorporating weak acid equilibriums and weak acid work. But we can actually have the same thing happen for weak bases. So just like with the other rules, the other things to keep in mind that we had written and we talked about in the first part is still true, right? We only ever transfer 1 hydrogen at a time. The ratio is always going to be 1 to 1. Same deal. If you're given the pOH, that's at equilibrium. If you're given a concentration, that's assumed to be initial. Okay. Now, your Kb expression is still exactly the same. Products over reactants, and we don't include our liquid water. Okay. Now, one relationship, and I think I have this coming up next, but we'll talk about this here. So one relationship that is going to be very important when dealing with weak acid and weak base equilibrium is this right here. So we know that Kw is equal to hydronium times hydroxide, right? But Kw also has a relationship with conjugate base pairings, acid and base equilibrium constants. So what do I mean by that? So when we have, when we're looking up the Ka values, right, we know our data chart at the back of the book has a whole bunch of different Ka values that you can look up. However, Kb's are not readily available. So meaning, unless they give you the Kb in the question itself, you will have to solve for Kb before doing the actual question. So this is when this relationship comes into play. So I'm going to write out our ammonia equilibrium so we can talk about this a little bit more in depth. Okay. So we know that if I were to set up a Kb expression here, it's going to be ammonium times hydroxide over ammonia, correct? So this would be the Kb for NH3, right? The actual weak base. Okay, well, the weak base for the NH3 value is not available in your data tables. However, we do have the Ka value of its conjugate. So just to remind you that the conjugate pairing for this question would be ammonia with ammonium, and then of course water with hydroxide. So when you're dealing with this, if you had to get this Kb value, what you would have to do is get the Ka value of its conjugate to determine it using this relationship. So if I have, so Kw is equal to Ka times Kb. If I want to solve for Kb, what I would do is Kw and divide it by the Ka value of its conjugate. So the Kb of NH3, I would have to do Kw, which is 1.0 times 10 to the negative 14, divided by the Ka value for ammonium. So this will work the same way no matter what. If you want the Kb for a certain weak base, you need to use the Ka of its conjugate. This we can look up in our reference tables and determine your Kb using this relationship. Okay, so I know it's kind of confusing, but honestly, it's just very similar to what we just did before, except it's an additional step. Instead of being able to look it up right away, it's an additional calculation that has to get done first. Okay, so here this is explaining that entire thing that we mentioned. So when you want, if you're given a problem that has a weak base from the relative strengths of your acids and bases, you cannot look up the Kb value, but you are able to look up the Ka value. So by understanding the relationship Ka times Kb is equal to Kw, of course, we're talking about at 25 degrees, it being this number. So remember, Kw can change at different temperatures. Of course, they will have to give you that value depending on whatever it is, but it's always assumed unless told otherwise. Okay, so this is what I just mentioned from before. So let's say, you know, we have, I want the Kb for fluorine ions. I would have to look up the Ka for hydrogen fluoride or hydrofluoric acid, right? If I want the Kb of acetate, I would have to look up the Ka of acetic acid, right? So you always look up the Ka of the conjugate. Now, similarly, you can also do it using the p-values. Remember, we have pKa plus pKb is equal to pKw, which is equal to 14. So if you have the Ka value and you do the pKa, if you subtract from 14, you can also get the pKb and then do 10 to the negative of that value. Honestly, I feel like this is the much easier approach that you're going to use more often, but it will work out to be the same either way. Okay, so they're giving you an example using the Kb for ammonia versus the Ka of ammonia, like I mentioned. So the Kb for ammonia you can get by doing Kw over Ka of the conjugate. Okay, so let's take a look at some practice problems. Okay, so we have hydrazine, which is used in rocket fuel, airbags, we love it. I love it. Okay, so the Kb of hydrazine is this, boom. Okay, so they're giving us the Kb. This is so nice. When you get the Kb, it's a joy. Okay, so we want to calculate the pH of the solution prepared by dissolving 12.0 grams of hydrazine in a 500 milliliter solution. Okay, so I'm going to start off by writing out our equilibrium expression here. Okay, so we have hydrazine in water, which is going to be N2H5 plus hydroxide. Okay, now we are not given the initial concentration, so there's a little bit more work here for us. So you'd have to first calculate the concentration by doing the number of moles and then divide it by our volume. So let's take a look at that. I'll do it in a separate color so we have this here. So we have 12 grams in 0.5 liters. We want this in moles per liter. So the molar mass of N2H4 is 32.05 grams per mole. So that's going to give us an initial concentration of 0.7488 moles per liter. Okay, so now the rest of this is going to be very similar. So we have 0, 0, minus x, 0.7488 minus x, plus x, plus x, x, x. Okay, so our Kb expression is going to be x squared over 0.7488 minus x. And I'm actually going to continue this in the next part of the video. I know this is a long one today, everyone. But I mean, it is what it is. You get some long and some short. We'll see you in the next part.